A baseball player slides into third base with initial speed of 4.2 meters per second. So this is first base, second base, third base, home plate. A baseball player comes running, he's sliding down, we'll say head first. I tell you not to do that. His hand should be ahead of him, but that's okay. He's sliding down into third. Has initial speed, when he dove and hit the ground, has initial speed 4.20 meters per second. A baseball player slides into third base with initial speed of 4.2 meters per second. If the coefficient of kinetic friction, you're sliding, that means you're moving, so it can't be static friction, kinetic friction. Mu k, the coefficient of that between the player and the ground is 0.43. How far does the player slide before coming to rest? How far? What is delta x equal to? And let me read again. How far does the player slide before coming to rest? What does that mean, coming to rest? Final velocity is what? 0. Remember the equation we had there. You really need three things to get the fourth one. Here you only have initial velocity, final velocity, and you're looking for delta x. If I look at my equation, there's one that will get me there, but it's missing something. This one. Right? I know what my final velocity, which is 0. I know what the initial velocity, which is 4.20. You gotta square it. Plus 2 times, I don't know what A equal to, and I don't know what delta x is equal to. I'm looking for delta x. So I can't solve for delta x if I don't know what A is. The other equation to use, you might be thinking, x equals, maybe I can use this. X equals x of 0 plus v0t plus 1/2 at squared. Remember, I'm looking for this. This is even worse. Why? Because I don't know what t is and I don't know what a is. I got three unknowns in it. I can use v equals v0 plus at, maybe this equation. How many unknowns in it? 2. And it doesn't even solve for delta x. So if you try any of them, they're not going to get you there because you're missing one more unknown. You need 3 of them to get the fourth one. All the equation we did before, you need to be given 3 things and you're looking for the fourth one. Here you are given 2 things and you're looking for the third one. So that doesn't do me any good. But there's a reason why they gave us mu k. Maybe from this, maybe I can find the acceleration. So let's see what's happening. The person is moving this way. He's sliding this way, right? That's the direction he's moving. Then there is a friction force pointing which direction? Backward. And the friction force Fk equals what? Mu k times the normal. The object is moving to the left. That means I can use Newton's second law. The net force equals mass times acceleration. What is the net force? You move into the left. So left, since you're going to the left, that's the positive direction. The net force is going to be what? What is the forces to the left? To the left. Do we have anything to the left? No. Minus. What's the forces to the right? The friction force, right? Let's write Fk for now. equals, that's the net force. Nothing to the left is the friction force going backward, equals your mass times the acceleration. Minus, what is Fk? Fk is mu k times n. They never told us how heavy that player is. Could be Mookie Betts, who is really skinny, or could be the panda, who is a little bit chubby there. Which one? Never say anything about the mass. Talking about the Red Sox players here. Could be Big Papi. He's about 240, 250 pounds. Mookie Betts probably 120 pounds when he's wet. You know? How come the mass was not given? Because the mass is not an issue. Why? What's the normal force equal to? Isn't that the mass times the gravity? You're laying on the ground. Let's say it's Big Papi. He's laying on the ground. The ground's pushing up on him with the same as his weight down. So the normal force here is mass times gravity. That's what the weight is. If you look at Big Papi laying on the ground, we have the weight down, which is mass times gravity, and we get the ground pushing up on him. So we know the normal has to equal his weight. And that's why they never gave us the mass, because the mass is not an issue. They cancel each other out. It's on both sides of the equation. Minus 0.43 times gravity 9.8 equals the acceleration. So we know he was slowing down. The acceleration has to be negative. Is that 4.2? Now you come back and you put that number into this one. How many unknowns do we have there now? Only one unknown. $17.64 minus 8.4 delta x. 8.4 delta x equals 17.64. Can we get what delta x equal to? Divided by 8.4, which is 2.1 meters. So Big Papi, Dustin Pedroia, whoever the player is, gonna slide 2.1 meters before they come to a stop. You know it's not Big Papi because he's running at a speed of 10 miles per hour. There's no way Big Papi can run that fast, you know? That's 6.3. Let's look at 6.28. Ah, that's a spring there. In case you forgot that one, you got a board attached where there's a spring, and somebody compressed the spring in. Somebody pushed on the spring. And they actually drew some pictures for us. They're saying, you know what? There's, if you look at the forces, there's the weight, which is mass times gravity. There's the static friction, F static, These were drawn for you. There is the wall pushing on the string is called the normal force. And there's you pushing on that string, F, with your hand, pushing on it, compressing it. A spring with the force constant, that's K, force constant. K for the spring is 140 Newton per meter. Is used to push a 0.24 kilogram block of wood. So the block of wood, the mass of it, 0.24 kilogram, against the wall. This is as shown in the picture. Find the minimum compression force. So what is F, minimum? Because once you exceed that, that wood is not moving. If I take a calculator, put it against the wall, it's going to fall down. I got to push on it a little bit to hold it from sliding. If I increase that pushing, it's still not going to slide. But there's a minimum value that's going to keep it from sliding. If I reduce that, it will fall. So we're looking for that minimum value. So let's write what we know. We know the coefficient of friction between the block of wood and the wall. That's mu s here. I'll put it here. Mu s equals 0.46, I think. Yep. Actually, they're not looking for the distance. They're looking for, they're not looking for the force. It says find the minimum compression, delta x, which is related to the force anyway. How much you have to compress it. Well, if you know what that force is, force equals negative kx, that will tell us what the value is. Now I can jump and answer question B there. It says, do you think that force will be different if the object was heavier? Again, imagine this, the wall standing up. I'm going to hold this calculator there. That would be probably less force than if I was trying to hold 100 kilogram or 25 pounds weight. Try to hold against the wall. If I use one finger, I'm not going to hold it against the wall with one finger. That thing is going to slip down. So if the object is heavier, I'm sure that force will have to be larger. Yes, it will be a different value. So I can jump and answer part B. Does your answer to part A changes if the mass of the block of the wood is doubled? Of course it will. Heavier object can require more force on it. But we'll see here. Let's write the forces again. Here we go. We get the weight down, mass times gravity. The mass is 0.24. Gravity is 9.8. What's that, 3.5? 2.4. The compression force here, you're pushing on it, on the wall. So your hand is right there, which means the spring wants to go backward, but your hand's stopping it. That means the spring is pushing forward on that piece of wood there. And the value of that force is pushing on it. The value of it is K times X. The direction tells you which way it's pushing. So when you compress that spring, it has two forces. One on the wood forward, one on your hand backward. The one on your hand will be the minus because it's pushing back on you. The one on the wood is pushing forward. That's really positive K times X, or delta X. We got the normal force, which is in this direction. And what's the value of that normal force? What do you think the value of that normal force has to be, value-wise? We know the direction, K times X. They have to be equal. If that thing is not moving, they better be equal. What else we got? We got static force, static friction, which is µs times n. Now the question is, find the minimum compression of the spring needed to keep the block from falling. That's the key. To keep the block from falling. Was the block moving up and down? Keep it from falling. Does that mean the block moved? No. If the block didn't move, that means what? The weight must equal what? The static friction. The force down should equal the force up. If you take all the forces down, should equal all the forces up. What do we have down? The weight. What do we have pointing up? The static friction. Well, what is your weight? Well, the weight of the block is 2.4 Newton. What is the static friction? It's µs times n. And let's fill in the blank. 2.4 equals, I don't want you to get confused, that n is Newton here, so I'll keep the units out. I don't want you to think that n and n can cancel. Equals µs, what's µs? 0.46. And what is the normal force? K times x, or delta x, right? Do we know what K is? Times K. K happens to be what? 140? Do we know what x is? No. How many unknowns in that equation? One unknown. Well, actually, let's do this in 2 steps. I have no problem doing 1 step, but I'll go slow. 0.46 times the 140, 64.4. And to get x, what are we going to do? Take the 2.4 divided by 64.4. Notice that 2.4 divided by the 64.4. 0.037. Which is roughly, that's meter, and that's 3.7 centimeters. So you have to compress it 3.7 centimeter. Now just think about this. It says, if the mass double, well, if the mass double, the only thing that's going to change is this one. This becomes double. So when you look at that equation here, this didn't change. The friction didn't change. K didn't change. If this number is double, would x be a different answer? Absolutely. It will be larger. So double that number and see what will happen. I bet you that'll be what? 7.4 whatever centimeters? Okay, that's 6.28. Where'd you go? 6.29. Okay. That's 6.29. We have, that's your windshield, your car, there's a mirror here, and from it there's a tassel hanging, your friend's graduation tassel, there we go. It's dangling from the windshield, from the mirror there. The mass of that is 13.6 grams. Tassel, graduation tassel, hangs on a string from his rear view mirror. Okay. It says when you accelerate the spotlight, and so you stop at the stoplight and you step on the gas. Well, what will happen to that tassel? Normally it was like this, the tassel. It was in that position, right? Well, when you step on the gas quickly, it's going to go like this. You're going to see that string go like this. It's going to move back while you're going forward. When you accelerate from a stoplight, the tassel deflects backward toward the rear of the car. Explain why. We'll explain that in a minute there. And if the tassel hangs at an angle of 6.9 degrees, this is 6.9 degree right there. .9 degree. You can see that number. Relative to the vertical line, what is the acceleration of the car? Now, why does the tassel move backward? Well, it goes back to Newton's first law. If an object is stationary, it wants to remain stationary unless you apply a force to it. So that tassel is sitting there. You step on the gas, your car is going to move forward. That tassel wants to stay here. And if it was actually dangling in the air, what will happen? It will stay there till it hits the back shield of your car. But it can't because there's a string attached to it. After a while, the car is moving forward. That spring starts pulling on it. And now it's going, that's why it's on an angle. So what is the acceleration? Well, when you look at that tassel, let's look at the forces acting on it. Here's the tassel, this little dot. We get the weight of it down, which is mass times gravity. And the mass is what? 13.6 grams. Let's change it to kilogram divided by 1,000. Times 9.8. .133 in Newton. And you get the tension is attached to a string. The tension is pulling on it in that direction. And let's look at this angle. If this angle is 6.9, this one, what is this angle then? If that's 6.9, what's that angle? Anyone? No, the angle. 83.1. Why? Because they have to add up to what? 90 degrees. Because I like my angle with respect to the x-axis. This way I'm not changing x and y. So if I look at my free body diagram, this is what I see. I see the weight down. And I see the tension in this direction of 83.1. I like that angle better instead of the other one. Can I break it down to x and y component, that t there? So we're going to have the weight, 0.133. We're going to have a value in this direction, a value in that direction. The value in this direction, t cosine 83.1, and the value in this direction t sine 83.1. Now, if you're watching that tassel, the height of it really never changed. It never moved up and down. As you go on, that thing leaned backward, but still, and you're going now, it's leaning backward, but it's not going up and down like this. That tells me if you take the net force in the y direction is 0. Or if you take all the forces pointing upward, this should equal all the forces pointing down. What is pointing upward? T sine 83.1. What's pointing down? 0.133. Can we find the tension in that string? 0.133 divided by the sine of 83.1. Point 134 Newton. 13397, so 134. Since the car is going forward, was the tassel moving forward? Well, in the car, sure. The car is moving, so the tassel has to continue going with it. Right? Not up and down, but forward is moving forward. So if the car going to the right, that means the tassel was moving to the right with it too. Since it's moving, you can't say the force is pointing to the right equals the force to the left. That's only when it's not moving. This is moving forward, so we have to use Newton's second law. The net force equals mass times acceleration. Well, what is the net force? Because it's moving, the car is moving in that direction. What's the net force? The only force in that direction is what? T cosine 83.1. Equals the mass of the tassel, which is what? 13.6 divided by 1,000, whatever that number is. You have to change it to kilogram, times the acceleration. We know what T is. 0.134 cosine 83.1 equals 0.0136, is it? A. And we should be able to solve it for A. Divided by 0.0136. 1.183? 1.19. Yes.
On the 83.1 sine, what answer did you get? Because I keep getting like 0.99.
Which one?
T sine 83.1.
Equals 0.133. You get the sine of 83.1. And what is the sine of 83.1? 0.992, right? Then you got to divide now. Jason, you got to divide that number by that. So my acceleration, if you carry all the digits, my acceleration roughly 1.19. If you carry probably fewer digits, maybe 1.18. But 1.19 meter per second squared. Accelerating on the racetrack. Let me find where's that question is. accelerating along racetrack. Okay. The next question. We have a racetrack here. It looks like this. We have a racetrack. This is point A here. The car starts here. It goes to point B right here. It goes to point C right here. It goes to point D right here. And it goes to point E right here. A road race is taking place along the track shown. This is the track here. All of the cars are moving at constant speed. The car at point F, where's F? Oh, wait, there's more to the track. I didn't show the whole thing. Oh, sorry, the track comes around here. I missed the rest of the track. F is right here. Okay, let me go back and see. All the cars are moving at constant speed. What does that mean, constant speed? What's the acceleration? 0. Constant speed means acceleration 0. If the car at point F is moving along straight section, you can see in the picture here, okay, on the track, where the other cars are moving, not curved section, here, here, up there, down here, and down there. Let VA, the velocity at A, which is the velocity at point A, what can we say about the acceleration? What's the acceleration here of the car at that point? So let the velocity at be VA. What can we say about the acceleration? The acceleration is parallel to VA. The acceleration is perpendicular to VA. Direct, well, I should redraw this because I didn't think there was one here. Point A is really right here. And VA is the velocity here. Car is going boom in that direction. What can we say about the acceleration? Notice it's like going in a circle there. If you go in a circle, there's centripetal acceleration, A centripetal. And what is the centripetal acceleration equal to? Isn't it V squared over R? So if you picture this right there as a circle, part of a circle here, you and the radius R here, then the acceleration will be toward the center. The linear acceleration going in that direction, the speed is not changing in that direction. So constant speed, that means the acceleration in this direction is 0 there. That doesn't mean there is no centripetal acceleration. On this one, the acceleration is pulling you back in here. So the acceleration is perpendicular to VA. And is pointing which direction? Centripetal acceleration is called centripetal because what? It is center seeking. What does that mean, center seeking? It's always point toward the center. So in this case, the car is going this way, the velocity, the acceleration is going that direction. What's that angle between them? 90 degrees? It is perpendicular. E will be right here. So this will be the acceleration is toward the center. It's 90 degrees with VA toward the center for part A. Part B, at point C, there's point C. Again, the velocity in this direction is going this way. We'll call that VC, the velocity at point C. Again, this is part of a circle right there. The acceleration will be in this direction. Central acceleration. So it will be an acceleration. It's going toward the center, which means down. It's 90 degrees with the velocity pointing down toward the inside of the track. It is perpendicular, points toward the inside of the track. Correct. Now, at point D, is that what the next one is? Let's see what's happening. At point D, assume the car has a velocity in this direction, we'll call it VD. This is part of this circle, the radius here. So the centripetal acceleration will be pointing in this direction. So that'll be perpendicular to that, toward the inside of the track, no, toward the outside of the track. No, it's pointing to the right, not to the inside, to the outside of the track. This one here, we'll call the velocity VE. This will be toward the inside of the track. It's pointing toward that center. Oh, they're asking for point F. What about point F? Well, point F is not actually a circular path, it's straight. If you move it on the road straight with constant speed, what's your acceleration here? Acceleration is 0, constant speed. So that one has a 0 acceleration. This is assuming the last part. God, there's a lot of parts to it. Assuming that all cars have equal speeds. The speeds were the same. Which car has the acceleration being the greatest magnitude, the greatest value? Well, based on my picture, the one is going to have the largest value is which one? The one with the tightest radius, the smallest radius. And I drew mine actually wrong. This one actually on the picture, on the diagram, D has the smallest radius. On my picture, E will be the one, because I made the radius really small, but when I looked at the picture, D has the tightest radius, the smallest radius. So that'll be the fastest one. Let me type in D. Why? Because it's V squared over R. And if R is less, the acceleration is bigger. The least acceleration, looking at it, is which one? Counting F, F will be the least one. So I will say F has the least because it has 0 acceleration. Unless they're talking about the other points. If they're talking about the other points, then it will be the one with the largest radius. My picture is this, but on their picture, it's that one. See? I'll see if they want to count F. It says U is A, assuming all the cars have the same speed.
It did.
It did?
Yeah.
So I'm going to put F there. Does it matter if I put capital F, small f?
I use capital.
It took a small f too, changes to capital, yeah. It says, how many more parts to this one? There's one more part. Assume that the car at point A, right here, and the car at point E, right here, again, my picture is deceiving, are traveling along circular path that has the same radius. Now, if the car at point A moves twice as fast as the car at point E, how much larger the acceleration? If the velocity of this twice that, assume the radius is the same. If this actually velocity is doubled, became 2 times that, how big the acceleration will be? Is it 4 times? Why 4? When you square 2, what's the result? 4. So, for example, at point A, let's just use point E here. Assume the velocity equals Vx. And assume the radius equals r. At point A, the velocity is going to be twice that, so that's 2Vx. And the radius is the same. So the centripetal acceleration at point E is going to be the velocity squared over r, and the velocity is what? Vx squared divided by r, and what do you have? For this one, at point B, what's the acceleration? At point A, I mean. The velocity is squared over r, but your velocity is twice Vx. So what do you have? 4 Vx squared over r. Notice this number has a 4 in it, this doesn't. This 4 times that one. That's why it's 4 times the amount. So point A will have 4 times that amount. Good. That's done. Lots of parts to it, but there's not much calculation. So if these guys have the same radius, and this is twice the speed, the acceleration is 4 times that. One more question, then we'll take a break. I know you guys are all tired now. I'm losing my voice too. 655. Hopefully it has some numbers in it. It doesn't have 10,000 parts. Okay. You have a 1,400 kilogram car. You're taking it out for a spin. As you go around the corner of radius 50 meters. So this is R radius is 50 meters. There's your car. The mass of your car is 1,400 kilogram. With the speed of 17, when you went around the corner, your velocity or speed was 17 meters per second. The coefficient of static friction between the car and the road. So here we go. Static friction, US equals, you don't have good tires, 0.88. Okay. The question says, assuming that the car does not skid, what is the force exerted by the static friction? Assuming the car does not skid. That's really key here. What is F of S, the static friction force. Now there's nothing mentioned about the road is being banked. In car racing, because the cars travel high speed, if you don't bank the road, the car will go sliding off that road. There's no tire that will hold the car on the track for 280 miles per hour. So if you look at Daytona Speedway, it looks like this. And the reason the car wants to go upward now, you get the static friction pulling down. In addition to that, the weight of the car is pulling down to keep it on the track from going out there. That track was not accidentally bent like this. And you see it on highway, if you approach a section, some of them, the road is banked a little bit there. Not because the road is bumpy and all that, no. They bank that road to make sure you stay on that road as you make that turn, knowing you might be coming at 30, 40 miles per hour. So that becomes a factor. Here, the road is flat. So if the road is flat, when you look at it, really, when you look what's keeping you on the road, you got a force pushing you. Remember, from the swing, we showed you that swing. As you start to go faster, what happened to the swing? It wants to go where? To the outside. As you make that turn on the car, that turn on the road, your car wants to go in that direction. There's a force pushing you in that direction. And that force, it's mv squared over r. If you have bad tires, if it's icy that road, that car will go skidding in that direction because of that force. What's keeping you from going that direction is what? The friction force between your tire and the road. That's what's keeping you. And that's equal to what? Mus times n. Now, if the road is flat, this is my car. My calculator is the car. This is the friction. Notice it's going on the track. What is my normal force? No, the normal force. Just the normal. The ground pushing up on me.
Mass times gravity.
Correct, because the weight is down, the normal is up. So I got my normal force is really the weight of the car. Mus times the weight, which is mass times gravity. It's not banked. And if you want to keep the car on the track, if you don't want to skid, you want to make sure these forces are equal to each other. They have to be. So F of S has to equal mv squared over r. And you notice here probably there's no reason to give us the mass of the car, because F of S, Mus times m times g equals m times v squared over r. Since the mass on both sides of the equation, mathematically you can cancel them out. So I don't have to know how heavy the car is. That applies for a small car or a heavy car.
Didn't they give you the mass up?
I know, but I'm saying there's no need for it. Yep, doesn't come in anywhere. I can do the problem without it. Notice I'm not even going to touch the mass, but if I put it in, I'm fine too. But why put it in? Mus is what? 0.88. Gravity is what? 9.8. Was the road banked? Actually, I'm just asking. They're not asking for. We know all the pieces, right? All they're asking for is what that F of S. So I don't even have to solve for it, because I can't solve for it this way. Mus times m. I just leave it like that. That's why they gave us the mass, I guess. I thought they were looking for something else. F of S equals mv squared over r. I know what the mass, I know what the velocity, I know what r is. Is there a part 2? Looks like they gave us too much information there, unless there's some more to that problem. No, I think I don't know why they gave us the static friction and all the stuff. You don't need it. Because you can do it with that, which is what? 1400 times the velocity, which is 17, square it, divided by R, which is 50. It's 80, 92, two significant digits, 8100 Newton. Now, the question is, you might be wondering, could I use this equation? Well, not really. That's your maximum, remember? That's the maximum static friction. Mu s times n is your maximum static friction. And we said your friction force could be any number between 0 and that number. So if the car starts to skid, about to skid, I know it's the maximum value, but they're not saying that's the maximum speed you can make that turn. If they say what is the maximum speed you can make that turn, then I could use that equation because I need to have the maximum static friction. If that car is going 2 miles per hour, I can't use that equation because this is my maximum number. My friction is going to be way smaller than if the car is going 15, 17, 19, 20, 21, 22. So that's why I couldn't use that one. If they want to calculate what is the maximum velocity that we can make the turn at without slipping. So if I change that question to, let me add to it. This, by the way, let me plug it in 8100. Submit. Correct. Now if I say what is the maximum speed? Speed to keep me on the track, to keep from skidding. What is the maximum speed that keeps me from skidding? Then I can say that, let me find the maximum static, Fs maximum, and you want that to equal to mv squared over r. And that's mu s times mass times gravity the m's will cancel. That's why I'm surprised they gave us that value for mu s because there was no use for it in this example. 0.88 times gravity, which is 9.8, equals v squared over 50. Multiply both sides by 50 to get rid of the fractions. (50) times 0.88 times 9.8, 431.2, which means v will be the square root of that number. You can make that turn at 20.76 meter per second. And you're just pushing your luck there. Approximately 46.5 miles per hour. So on that turn, if you hit it at 46.5 miles per hour, if it's dry, you're okay. You go over that, that car goes skidding. That's the maximum speed.